So can you see the screen?
Yes, ma'am.
Okay. So last time we saw snake oil method. We saw several examples and we applied the snake oil method and obtained the result, right? Today
Yes,
we'll see what we had actually been trying to do, that how we can solve combinatorial identities. So suppose some identity like this is given to you. So some particular summation is equal to some other summation. And then you are supposed to show them to be equal to each other without evaluating any of the sums. So in such a case, what do you really do? Generally, what we do, we start from here and then, we keep on manipulating till you reach here, right? But
yes, ma'am.
the entire method of snake oil says you don't have to solve these. And that's precisely what is being asked in the question, that you show these two are equal without evaluating either of the two sums. So in such a case, what you do, you apply the snake oil method to this, you apply the snake oil method to this, and you see that the generating functions that you get, the ordinary power series generating functions, they are same, exactly same. So when the generating functions are exactly same, then of course their coefficients are going to be same,
Yes,
right?
ma'am.
So suppose fx is the generating function for this one and gx is the generating function for this one, then that really means that this is the sequence of coefficients for the generating function f, and this is the set of sequence of coefficients for the generating function g, right?
Yes,
So
ma'am.
if I can show that as generating functions fx is equivalent to gx, then I know that component wise they match up, which means the coefficient of x raised to n for f and coefficient of x raised to n for g, they are same, and that would prove this identity, right? So that is
Yes,
what we're going to see in this particular example. So if you start with this, let's say same method, what was it? What?
we should find a free variable first.
Free variable. So tell me a free variable in left hand side sum.
We can choose m or n, but I
Hmm.
think it's better to choose m.
Okay. And why is it better to choose n?
I mean, we have n plus k on the top, so like we can change that if we choose n to be a free variable.
And even better, m actually appears twice.
Yes, ma'am.
So it's always advisable. I mean, towards the end, we will see that is the whole discussion where it rounds up to, that whenever you have more than one occurrence of the free variable, then you should do manipulations and reduce the number of its occurrences. How we do that, we'll see later. But for here, why n is a better choice? Because it occurs just once. Okay.
Okay, ma'am.
Now, so if I start with this and apply my snake oil method, I'm going to get this double sum with x raised to n here. Now, as usual, I take the summation with k outside and summation with n inside. Rearrange the terms which are dependent on the respective summations and you get this. Okay, so I've already manipulated by putting a x raised to minus k and x raised to plus k here. Yeah.
Yes, ma'am.
Now, this identity which we have been using so many times since last class, it is x raised to this bottom element of the binomial coefficient divided by 1 minus x raised to plus 1 of this. So you get this thing. Now in this, 1 upon 1 minus x is free. So you can take that out. And what you will be left is the, okay, even x raised to m, and this entire thing is free because the summation is running over k. So m powers are all free. So you take x raised to m over 1 minus x raised to m plus 1 outside. and you have summation k, m choose k, 1 upon x raised to k. So instead of writing x raised to minus k, I've written 1 over x raised to k. And now this thing is, yeah,
This was the first identity we used.
sorry,
This was the first identity.
no, what does this translate to? What is this summation? Closed form formula for this summation?
So this is uh, 1 by x power k by 1 minus 1 by x power k plus 1.
See more closely. This is k and not m.
Oh,
Yeah, this one is. What is the formula for x plus y raised to n?
okay, okay, okay. Yeah, this is just 1 plus 1 by x raised to m.
Right. So you have x raised to m, this one comes as it is, and 1 plus 1 by x raised to m. Solve this entire thing to get 1 plus x. Oh, there's a raised to m missing here. So this is this raised to m over 1 minus x raised to m plus 1. Okay.
Yes,
Now you see the other side, which is summation k, m choose k, n choose k, 2 raised to k. Again, you will do the same thing. So since here you chose n to be a free variable, and that is why n does not appear here. Here also it is then advisable to choose n as your free variable and work with it. Even though here n and m both appear just once. Okay.
okay,
So you start with the x raised to n being multiplied and then summing over n positive, non-negative. Why? Because in the question itself we are given that. Yeah.
okay.
So we are here. You rearrange the terms. You have summation k, m choose k, 2 raised to k. All this comes out. Inside you have summation n greater than equal to 0, n choose k, x raised to n. And now this is equal to,
This is x power k by 1 minus x power k plus.
great. So this is what it is. Now this I write all together, taking 1 upon 1 minus x outside. Then inside I'll have m choose k, 2x over 1 minus x whole raised to k. Right?
Yes,
And now what is this?
this is 1 plus that term 2x by 1 minus x whole power m.
Right. So it is 1 plus 2x by 1 minus x whole raised to m. Solving this, you have 1 minus x plus 2x. So 1 plus x over 1 minus x raised to m. Right? Just collecting terms together, you have 1 plus x raised to m and 1 minus x raised to m plus 1. Isn't this equal to this? With, of
Yes,
course, that this is a bracket. Okay.
yes, ma'am.
So without even knowing what this number is or this number is, without doing any computations on these summations as it is, we manipulated a one step up and proved it that since the generating functions are equivalent, so are the coefficients. Okay.
Yes, ma'am.
So this is another way of giving a proof for combinatorial identities, where you actually don't really solve any of the uh, involved summations, but you still know the answer. But however, can you do any better? Like so far we have always been dealing with the ordinary power series generating functions, right? We always do a multiplication by x raised to n and then summation over all possible values of n, and then we do the rest of the recipe, right? But
Yes, ma'am.
can exponential generating functions be any better? Can they widen the scope for us? Can the exponential generating functions also be used for the snake oil method? We see now. So before that, just some notations which we have seen earlier in the course. Remember, we studied the Stirling numbers of both the kinds, first and
Yes,
second kind. So let's say the Stirling number of the first kind are denoted by the square bracket nk. Okay, round one is n choose k, square bracket nk are the Stirling numbers, and bk be the Bernoulli numbers. We have seen these also. Then there is an identity which you can try to prove. I will just list it here, that if you do a summation over n, then Stirling numbers of the first kind nk times xn over n factorial is equal to 1 over k factorial log of 1 over 1 minus x whole raised to k. Okay,
okay.
so this is identity which I am stating. You can try to prove it also, comes from the definition of Stirling numbers and the Bernoulli numbers itself. And then proceeding further, what is a hypergeometric series? It's a series summation ktk such that the ratio of any two consecutive terms is a rational function. Okay, so rational function, you know, right?
Yes, ma'am.
It's a ratio of two polynomial functions,
Yes, ma'am.
right? So whatever we have dealt with so far, even in this particular example, so it's oh, I should give enough time to things. So it's a rational function of k, whatever the summation is running over. It's a rational function of that particular parameter for every k.
Okay.
Now, here this one is a this is a summation running over k, and whatever you have as m choose k, n plus k choose m. So does this summation represent a geometric series? Sorry, hypergeometric series?
Should the function be fixed for every like?
No,
I
no,
mean,
no.
then yes, like
Of course,
because
function can't be fixed. No, if the function becomes fixed, you are actually saying that the summation is running over constant terms. Because you would say that tk plus 1 over tk is some alpha.
I mean some rational function, like a fixed rational function. For example, summation k bar n, like summation n bar k or something.
Yeah, but you already said that you are taking this for every k. So then how do you really do you say that tk plus 1 over tk is a fixed function of k?
I'm asking whether it is the case.
Yeah, that is what I'm just confirming with you. So is that the question?
Yes, ma'am. Yeah.
Okay, no, that doesn't have to be the that is not true. How it is defined is that it has to be a function, a rational function in the variable k.
Okay, ma'am.
Okay, for every different value of k, like for every different ratio tk plus 1 over tk or tk plus 2 over tk plus 1, this function will keep on changing. All we know is that this is going to be a rational function. If that happens to be true for every such ratio, consecutive ratio, then I mean ratio of consecutive terms of the series, then the series is called a hypergeometric series.
Okay.
Okay. So so what we said now here was that can we extract more out of the snake oil method if we tried applying it to exponential generating functions instead of the ordinary power series generating functions. And we see the answer to it now. So what happens is that many combinatorial identities that you see are actually special cases of identities in the theory of geometric hypergeometric series. So for instance, what you have seen so far, all the examples. So let me just open the previous lecture. Yeah. Can you see example 1 on the screen now?
Uh, I'm able to see only lecture 20 now.
Oh,
I think you have to reach. Yes, ma'am.
huh. So see this example 1. This was summation of k choose n minus k, where summation was running over all the non-negative values of k. So if you take any such summation, I mean, if you take any such entry, k choose n minus k, it's clearly a rational function in itself, right?
Uh, in K, ma'am.
Yeah, in k. So k choose n minus k is what? K factorial over n minus k factorial and n factorial.
Do we allow factorials in the CK?
Factorial is like when you just expand them, they becomes polynomial, no?
Okay, ma'am. Yes.
So write down the k factorial as the prod, as a sum of the different powers of k that comes out of it, right?
Yes, ma'am.
So clearly this is a hypergeometric series
Yes, ma'am.
because each of the terms itself clearly is a rational function, and when you take the ratio of two rational functions, you're again going to get a rational function,
Yes, ma'am.
right? The
Yes.
next example which we saw last time was this. Is this a rational function? Is this fn? Sorry,
Yes,
not fn. Is fn a hypergeometric series?
yes, ma'am.
Seeing the next example, this. What about this one?
How do you interpret -1 per K? Uh,
That anyway will get cancelled when you're taking just the consecutive terms. It only leaves a minus sign.
yeah. Then yes, ma'am.
It is
Uh,
also the one which we did after that.
Here we have K in the exponent, but is that okay?
Yeah, so see what really left is left out. So
In
this
the
one is
ratio
not
term,
going to create any problem that we agree upon. Okay, then we are
yes,
left with this part. So if you see this, let's say 2 raised to n minus k divided by 2 raised to n minus k minus 1. So what is really left?
yeah, we just have to.
Right,
So
that's not a problem.
yes,
So you see how important this is. This would not have been the case if I did not restrict myself to taking ratio of consecutive terms, right?
yes, ma'am.
Therefore, this also is going to give you not going to give you, this is a hypergeometric series.
Okay,
Okay. And the last case which we saw in previous lecture was this. Again, you might feel that, oh, this y raised to k might be a problem. No, y raised to k or y raised to k minus 1. So you're
yes, ma'am.
just left with a y, and that's a free variable for you. Yeah.
Yes, ma'am.
So this is what. So whatever we have seen so far, all those examples were of the hypergeometric series. Now we come to something which may not be a hypergeometric series. However, snake oil method still works. Okay. And there are some general tools for dealing with sums of this kind. If you want to see a further discussion of these tools, you can read this article by Ranjan Roy. It's binomial identities and hypergeometric series in American Mathematical Monthly.
Okay, ma'am.
Okay, so now in question, the sum that I want to deal with is this. So Fn is summation over k, Stirling number of the first kind nk, and product with bk, where bk is the Bernoulli number, kth Bernoulli number. Okay, so then this is not a hypergeometric series, right? And in such cases, when we are not getting hypergeometric series, we surrender ourselves to the snake oil method, but not for the OPSGF, but for the exponential generating functions. All right. So you let fx to be exponential generating function for the sequence given by fn, and then apply the rest of the recipe as it is.
Okay, ma'am.
What is the rest of the recipe? So
We
if
choose a free
fx is
variable.
your, fx is the EGF, so then of course you would have taken fn, multiplied it with x raised to n divided by n factorial, and then sum over all possible values of n, right?
Yes, ma'am.
That was the difference between the OPSGF and EGF. So then fx is equal to this, and then you put the value of fn here, and then do what?
Interchange this.
Interchange the summations. So I've put the values here, and then I interchanged the summations. So summation n was outside, I took summation n inside with things that depends on n here, and whatever didn't depend on n comes out in the summation for k. And now this, I already told you that this identity evaluates to 1 upon k factorial log 1 upon 1 minus x whole raised to k. Okay,
Yes,
this is what I had given here. All right.
yes, ma'am.
With this, so I get this expression, and now if I take log of 1 upon 1 minus x as u, what I actually have is summation k bk u raised to k over k factorial. And this you have seen earlier in, I think, one of the initial lectures when I had given you a long list of famous identities. This evaluates to u upon e raised to u minus 1. Okay, for you to recall, I've put it down here also.
Okay.
So even though this k is k doesn't have a value here, and this one has a sorry, k doesn't have a range here and k has a range here, I've still applied and written this down here. Why?
The B Ks are zero for k less than zero.
Right. And also this factorial would not make sense for negative
Yes.
numbers. So once you have u over e raised to u minus 1, you put back the value of u, which was log of 1 over 1 minus x. So you get log of 1 over 1 minus x, e raised to log. So this is a natural log. So e raised to log of something evaluates to that something. So you have 1 over 1 minus x minus 1. Oh, so this bracket, this looks a little confusing. This ends here. Okay, this is not equal to this. This is a separate chunk.
Okay.
Okay. So, oops. Yeah, very quickly we'll finish today. So then you are actually left with 1 minus x over x times log of 1 over 1 minus x. And now you know the expansion for log x, right?
Yes. Sir.
The series expansion. And then with this product, you can find out the coefficient of x raised to n in this. And coefficient of x raised to n in this function is n minus 1 factorial over n plus 1. Therefore, what I started with, this particular summation here, is actually n minus 1 factorial over n plus 1. And thus we have evaluated the series Fn, even though it was not a hypergeometric series. Okay.
Yeah, like uh, we could have done the ordinary power series generating function also, right? But that wouldn't have been this easier.
Yeah, like it, the, so to say, the, how should I put it? You can always start with the ordinary generating function. Okay. And then as you proceed along, so see here at each step, the things gets tidier and tidier, right?
Yes. Yes.
And when it stops happening this way, you know it's not going to lead you to a nicer route,
Yes.
because ultimately our aim is to find a closed form formula for Fn. Some particular formula for Fn is anyway known to us. That is what we started with. We want to simplify and find a closed form formula for Fn. So the generating function should be chosen cleverly enough so that the manipulations that we do, in the sense of after interchanging the summations, the term should be nice enough to evaluate further.
Yes.
Right? For instance, if let's say we didn't know that this thing is equal to this thing, then we would have been stuck at this level.
Yes.
So similar thing would happen even if you start in a wrong direction. Wrong in the sense, something which is not going to lead you maybe as peacefully as the other way would have led you to.
Okay.
Okay. And that is why whenever you are not dealing with Fn, small fn, which is not a hypergeometric series, it is advised to use the exponential generating function for that small fn instead of the ordinary power series generating function.
Okay, ma'am.
Okay. So yeah, this is the end of the examples. And as a final remark, what I stated in the beginning of today's lecture also, is that sometimes the free variable occurs more than once in your equation. And in such a case, then it would be hard to evaluate it. Why? Because you always take the summation of n inside, right?
Yes, ma'am.
N is the free variable for you, then the summation of n after being interchanged with the summation over the thing which is there in small fn, the summation over n is inside, or equivalently summation over n is the thing which is evaluated first.
Yes,
So
ma'am.
if n appears more than once in your equation, then what really happens is that there are more terms of small fn that depends on n. Therefore, there are more terms which appear with the summation over n, and now they need to be evaluated first.
Yes, ma'am.
And that makes life harder because most of the identities that we know or deal with appear with the for instance, whenever you have, where is it? So for instance, even this. So here, if I had chosen m, then m was to appear here and here. And then when I have to evaluate the summation over m, I would have a m choose k and n plus k choose m both together.
Yes, ma'am.
And very few identities whose closed form formula we know are of the form which take two of the binomial coefficients at the same time.
Okay, ma'am.
So cleverly enough, we try to reduce the number of terms dependent on a free variable. But how do we really do that? So what happens is you start with the this you can see. Yeah. So the sums which you are dealing where the free variable appears more than once, you introduce dummy variables, dummy free variables. Okay. So whenever some n, let's say n and n plus 2, n plus 3, etc., are appearing, you replace n plus 2 by some m, n plus 3 by some p, n plus 4 by some q, and so on. And now all this m, p, q, all are your free variables. So what it really does is, it so whatever you would have evaluated for, let's say, the equation which the series which involved as free variables, the variable n, m, p, q, r, it's going to have the original series as a special case.
Yes, ma'am.
So for a particular value of q, for a particular value of r, for a particular value of p, m, etc., it translates to the original series.
Yes, ma'am.
So after introducing these dummy variables, the series may not look so familiar or nice to you because it has translated into its general form. And as it may be taken as a fact that in the subject of these combinatorial identities, it is more often than not, it's easier to prove general theorems as compared to their special cases. Okay. So
Okay.
because the special cases will have this limitation that you have to work with lesser number of variables.
Yes, ma'am.
So you keep on throwing in the dummy variables and then come to a particular summation that will have lot of possibly free variables, and that is why we were not worried even in last lecture when we had more than one free variable. We just chose one and we went ahead, right?
Yes, ma'am.
So by introducing this dummy variable, you actually translate the identities to their general form. So for instance, if you have this particular geometric hypergeometric series, summation over I, n choose I, 2n choose n minus I. So n is the only free variable in this,
Yes, ma'am.
right? So I do not have any way out. I will have to choose n if at all I want to apply the snake oil moth method, or I will say, oh, I cannot apply snake oil method because the free variable occur more than once. But before giving up, the application of snake oil is valid even here by doing what? Introducing gummy variables. Okay, so it's quite easy to suppress this particular shortcoming of the snake oil method. Like this is a sneaky way out. The limitation of snake oil method is that you should not have the free variable coming more than once. So you would feel that you can't apply, but then if you just rearrange these terms or like relabel these terms to some new different free variable, then we have the answer. So for instance, if I let 2n to be m, and this n now is replaced as r, as it is. I did not say n minus I is r. I said n itself is r. Then you have this particular equation, and can you solve this with the snake oil method now? Yes, sure.
Yes, ma'am.
So that is how we deal with the series that have occurrence of free variable more than once. Okay, and there are still a few limitations to the snake oil method, and the next general version or like a more advanced tool for solving such summations is the WZ pairs, which I briefly mentioned in the last lecture also. But since anyway that is also hardly one lecture's material, I will stop today's lecture here itself, and then next lecture we'll see on Wednesday where we'll cover the WZ pairs.
Okay, ma'am.
Okay. Okay, rest is the same thing written which I've said. Huh. Okay. Yeah. So any questions?
No, ma'am.
Okay.
So we will have a class on Wednesday, and will that be
Sorry?
the last lecture? The next class will be the last lecture, is it?
Yeah. Today's is the second last. Wednesday would be last. Next Wednesday.
Okay, ma'am.
It's going to be 22.
Yes.
On 22, we'll have last lecture.
Okay,
Okay.
ma'am.
ठीक है, चलो.
Thank you, ma'am. Bye.